Hi, this is Bruce Jameson from ASARC at the University of Calgary, and this is a presentation based on a paper presented at the Geohazards 6 conference in Kingston in June 2014, and my co-authors on the paper are Rudy Beglinger and Doug Wilson. In February 2011, Rudy Beglinger contacted me to say he had observed a large avalanche on Mount Tumbledown. He thought it was a size 5. Could I look at the data and comment? Well, absolutely. So the early part of this talk applies the avalanche size classification that we've used in Canada for 33 years to the large avalanche on Mount Tumbledown. This size classification is based on the destructive potential and has been adopted by some other countries. It's been a great success. In recent decades, I've had many stimulating discussions with a variety of people about this classification. Some thought size was often underestimated, others thought the typical deposit mass for size 4 and 5 avalanches could be larger. Some of these conversations were with Doug Wilson from BC Ministry of Transportation and Infrastructure. He said he had a large data set of avalanches with estimates of deposit volume. By estimating deposit density, we could compare these to the typical mass for size 4 and 5 avalanches. There were two other size classifications we could use for the comparison. A recent one from the European Avalanche Warning Services, and an older one from 1980. Based on these comparisons, I'll finish with some thoughts on the classification of avalanches based on destructive potential. This paper, which is online, covers these points and others in more detail. Here is the south side of Mount Tumbledown. The black outline shows the outline of the avalanche, which ran for 3 kilometers. Up to this orange dashed line, there was consistent evidence of a powder blast. Up to this pink dashed line, there was some evidence of an air or powder blast. The crown was 600 meters wide and reached a maximum depth of 8 meters. Here's the track of the avalanche here, where simple dynamics models indicate it reached a maximum speed of 60 meters per second, that's over 200 kilometers per hour, and an impact pressure of 900 kilopascals. In Cairns Creek, you can see the avalanche came down, and some of it followed the creek and some swept wide up onto this bench where it destroyed a forest including 200-year-old trees. Here we see some of the trees felled by the avalanche. In the fair weather that followed, Rudy and his staff were able to get out on the deposit and make detailed measurements. Looking down on the avalanche, the black line shows the outline of the dense flow avalanche. The orange dashed line here shows where the evidence of the powder avalanche reached, and there was inconsistent evidence of a powder blast out through to this pink dashed line. The black dashed line shows the deposit area, and the total area of that was 20 hectares. This gray area here, here, and here are where trees were seriously damaged or destroyed, and they total 20 hectares. There was an additional 20 hectares of areas where trees, had they been present, also would have been destroyed. The deposit depth was measured at 4 places, 17, 20, 25, and 32, and this was based on altimeter readings between the surface of the deposit and the creek using a reference of an exposed rock down here. If we approximate the area of the deposit by 2 rectangles, we get an area of about 20 hectares. If we assume there is about 3 meters of snow already on the ground, and the average deposit depth was 20 meters, that's 17 meters, we get a deposit volume of about 3.3 million cubic meters. Assuming a density of about 400 kilograms per cubic meters, which may be a little bit low, we get a mass of 1.3 million tons, which is at least an order of magnitude above what is the typical mass of a size 5 avalanche. And suppose the average height of the deposit was only 10 meters, then we're still in the right range for a 10 to the 6 tons, which is about an order of magnitude above what's necessary for the typical mass of a size 5 avalanche. We have to get down around a deposit height of 1 meter before we have the typical mass of a size 5 avalanche. Here are the definitions for a size 4 and a size 5 avalanche. Looking at the definition for a size 5, the avalanche destroyed 20 hectares of forest, and looking at the previously cleared areas, it could have destroyed an additional 20 hectares of forest. The deposit mass was an order of magnitude larger than the 10 to 5 tons associated with size 5 avalanches, and the avalanche ran 3 kilometers. So it was clearly a size 5. Nevertheless, some practitioners question whether it was a size 5, perhaps because there are much larger avalanches known in areas such as the Himalayas and elsewhere, or perhaps because there is a tendency to underestimate destructive potential and hence avalanche size. Just to help us visualize 40 hectares, here's downtown Revelstoke, and the red rectangle here outlines 40 hectares. So we see 40 hectares is a good chunk of downtown Revelstoke. In the next couple slides, I'll compare the destructive size scale with the BC Ministry of Transportation data. And just as a reminder that the landmark paper by Dave McClung and Peter Scherer in 1981, they had 744 avalanches from Rogers Pass with measured volume and calculated mass, and we'll be comparing that with the data set from the BC Ministry of Transportation Infrastructure. They had over 35,000 avalanches with estimated volume, but only a handful with measured volume. Doug Wilson provided records of 5 avalanches for which the deposit was first estimated and then measured. Here's an example of a measured deposit in which different colors show different deposit depths. For these 5 avalanches, for which the volume was first estimated and then measured, the estimates of deposit volumes averaged 80% more than the measured volumes. Roughly, the estimates are about twice the measured volumes. In the next slide, I'll mention this overestimation and show that even if the Ministry of Transportation volume estimates were halved, it would have little impact on the way the data compare to the 3 size scales. This graph compares deposit volumes from different sources. The avalanche size from 1 through 5 lies along the x-axis. The deposit volume on a log scale lies along the y-axis. The purple boxes are deposit volumes from the 1981 classification used in Canada and elsewhere. These are estimated with plausible values of deposit density given in the paper. The black bars are from the European scale. The white boxes are from Ron Perla's 1980 scale. And the orange boxes are from the BC Ministry of Transportation dataset. Because there are likely errors in the recording errors showing up in the whiskers, we concentrate on the orange boxes, which represent the middle 50% of the estimated volumes. For size 1 and 2 avalanches, we see good agreement between the 1981 classification and the European scale, and with the estimated volumes from the BC Ministry of Transportation. The volumes from Perla's 1980 scale are lower than from the other 3 sources. Looking at size 4 avalanches, we see the deposit volumes estimated from the 1981 scale are lower than in the European scale, lower than in Perla's 1980 scale, and lower than in the BC Ministry of Transportation estimates. As mentioned, these BC estimates could be shifted down by a factor of 2, but that's not far on this log scale. Looking at size 5 avalanches, we see the volumes from the 1981 scale are lower than from Perla's scale, lower than the volume estimates from the BC Ministry of Transportation, and we can't compare with the European scale since it only provides a lower limit for size 5 avalanches. The previous slide shows deposit volumes associated with size 4 and 5 avalanches from the 1981 scale of destructive potential are lower than the data from the BC Ministry of Transportation. This could be due to the destructive potential being underestimated. However, regardless of possible underestimation, the comparisons with other size scale suggest that the values of the typical mass for size 4 and 5 avalanches in the 1981 scale of destructive potential could be increased. The paper goes into these points in more detail. So, in summary, size 5 avalanches are more common than many practitioners think. One of the columns in the definition is for destructive potential, and we've tended to put a lot of weight on that, but it is the most subjective column, and that probably contributes to our underestimation of the size. The columns for the typical mass and the typical run length are underutilized. The BC Ministry of Transportation Highways dataset has shown quite nicely that size correlates well with deposit volume. We can get estimates of deposit volume from deposit area and the estimated depth, and we can get the deposit area by drawing an outline of the deposit on Google Earth. We could add a column for typical volume, and it could supplement the definitions for typical mass in the size definitions. We presented an argument here, and it's presented in more detail in the paper, that the typical mass in the destructive size scale could be larger for size 4 and 5 avalanches, but that should not be done without a thorough technical review. And to supplement this short talk, there's also a separate video covering a practitioner survey. I've mentioned the paper a couple of times. You can get it at the link on the screen there. You can press pause so you have time to write it down, or just do a web search for avalanche size classification Selkirk. Over the last 10 or 20 years, I've had many wonderful discussions about the avalanche size classification with the people on the screen, and my co-authors and I would like to thank them.